a quick summary of what we said in the last week or 2 weeks ago. We started out with a structure. In this example, it's the rational numbers with order. And then based on that structure, we could build like data structures which were sets. In this example is I take all rational numbers such that A is smaller than B, but it's smaller than 3. And for each such pair, I consider the open interval that begins in A and ends in B. So this is the family of all open intervals such that the later endpoint is at most 3. So this is a typical data structure I could construct. Things of this form were called set builder expressions. And you could do set builder expressions for any structure. It didn't have to be decidable, didn't have to have any properties. And then you could manipulate them, and essentially manipulating set builder expressions was the same thing as manipulating first order formulas. So in particular, if your structure, such as this one, had decidable first order theory, which means that if you write a formula of first order logic, such as this one, and then you can ask if that formula is true or false, and there's an algorithm which tells you. So some structures have a decidable first order theory, some don't. This one does. So we could write set builder expressions, and one of the results was that if you had two sets, both of them represented by set builder expressions, then you could ask if it's the same set, and this would boil down to, you could, based on the sets big X and big Y, you could write a first order formula, and they would be equal if and only if this formula would be true. So in particular, if this structure had decidable first order theory, then you could ask if two sets are equal and if one set belongs to another, and you could work, essentially you could work with these sets. That was one side of the story, the syntactic side, set builder expression. But there was another side of the story, which was the semantic one. So let me write this. And the semantic one was the following. We would consider sets which are, well, hereditarily, because the set has elements and elements and elements, you might, but the central property was finitely supported. So there were two properties, 1 and 2 orbit finite. So let me remind you what those properties meant. So first of all, what does it mean for something to be finitely supported? In this case, a set. It meant that there was, I should have a color for examples, but this meant that X is finitely supported, or maybe more precisely, a tuple of atoms is a support of a set X, or generally an object X, if for every whenever you take some automorphism of the underlying structure, then if two automorphisms agree on the tuple, then they also agree on the big X. That means that the tuple A is a support of big X. Okay, that was and if you remember, there was this more abstract view that it just belongs to sets with group actions, but there's no need to remember that. Okay? And for example, this set here, if we take it to be big X, then you can see that it's supported by 3. Because if you take any automorphism of these atoms, which is an order-preserving function of the rational numbers, And if it doesn't move 3, then it won't move the whole set X, the whole set of open intervals. And we analyzed this. Okay? So that was the first condition. And orbit finite meant that X is orbit finite if it has finitely many elements up to automorphisms. So again, if you remember, there were two ways of understanding this vague text. One was I could say up to all automorphisms of the structure, and then the orbits become bigger. So it's easier to have finitely many elements up to all automorphisms of the structure. And then an alternative understanding was that you fix some tuple of atoms and you only talk about automorphisms which preserve that tuple of atoms. So it's harder to be an automorphism. So there's fewer of the automorphisms, and therefore the orbits become smaller. And then there was a theorem which said that maybe I put it makes sense for oligomorphic A. And what does A mean? Oligomorphism mean? Means that A square have finitely many orbits with respect to all automorphs. And then under this assumption, this statement here could be interpreted in several different ways, and they will all be equivalent. And I will only talk about orbit finiteness under this assumption of oligomorphism. That's a summary of what we had last time. We had these two notions. We even showed the top-down implication, which was kind of easy. Essentially, you're supported by whatever is written in you. And then you have, and from the assumption that something is oligomorphic, you're going to have finitely many orbits. And this was kind of easy. Now I would like to discuss a little bit today the bottom-up implication. Okay? I will not do it in full detail, but just to give you some of the ideas and to present the connected model theory result, which is used here, so that you will see the connection. So, can I move here? Is it okay? So let's continue with the bottom-up implication. If you're really cool, you can do it like in one line, but I couldn't master this skill, unfortunately. So let's do a special case of the bottom-up implication. And let's take, let X be a set of tuples of atoms. So it's not some abstract set of sets of sets of sets of sets, but it's a set of tuples of atoms of fixed dimension. And be equivariant, which means supported by the empty tuple, which means that it's invariant not under all automorphisms. So X belongs to big X if and only if pi of X, okay, for all automorphisms. So it's invariant with respect to automorphisms of the structure. Okay? So this is a special case of the bottom-up assumptions. Why? First of all, is big X finitely supported? What's it supported by? Well, it's just written there, by nothing, by the empty tuple, yes? Because you apply any automorphism, you take any two automorphisms, pi and sigma, and you apply them to big X, you get the same result, namely big X. Okay? So it's finitely supported. Is it hereditarily finitely supported? I just discussed big X itself being finitely supported, but I should also argue that the elements of X are finitely supported. But what's an element of X? An element of X is like a tuple, like 1, 2, 5. That's an example of an element of X. What's this tuple supported by? 1, 2, 5. If I know what an atom automorphism does to 1, 2, and 5, I know what it does to the tuple 1, 2, 5. Okay, so it's automatically hereditarily supported. Is it orbit finite? How many, well it is, well I don't even have to discuss this at any time, it's just a direct corollary of the assumption on oligomorphism, which says that, the entire space has finitely many orbits. Okay? Is it hereditarily orbit finite? So how many elements does this guy have up to atom automorphism? Okay, that is a little bit stupid question, because if you think about tuples in the normal way, it has no elements, because this tuple doesn't have any elements. Yes, it's a tuple. It's not literally true, because if you go through the pedantic meaning of what a tuple is, it's encoded as a set of sets of sets of sets. There's some way to do it. So it, technically speaking, will have elements, but it's going to have like the elements are going to be, I think, 1. There will be an element like 2, and maybe 2, 5 is going to be an element. But there's going to be like finitely many elements altogether. This is just pedantism, so it's going to be orbit finite. Anyway, so this is a very special case of a set which is hereditarily finitely supported, because it's equivariant and its elements are finitely supported. It's a very special case of an orbit finite set. It's not a very special case, as you will see later on. So actually, most of the proof is already happening here. So what should I do? In order to prove the bottom-up implication, I should prove that it is described by a set builder expression. Yeah? So if the bottom-up implication is true, there's a set builder expression which defines it. Now, what that really means is that, and we're going to show, well, we will say then X can be defined by a formula of first order logic. So this is the lemma that we're going to prove now. That if you have a set which has this semantic property that it's invariant under automorphism, then necessarily it can be defined in first order logic. And this is going to use this assumption of oligomorphism. It's not true in general. I mean, you take, for example, the atoms are, say, the natural numbers with order. So you think about it a little bit, which sets are definable in first order logic? When can you define a property of a natural number in first order logic in this structure? If you think about it a little bit, then essentially there's nothing you can do. It's only, you can say maybe a finite set or a cofinite set. I mean, for big enough numbers, like from first order logic, there's no difference between 1,000,000 and 1,000,001. So if the formula has size at most 10, then it won't make any difference between numbers bigger than 1,000 and 24. Okay, so here first order definable sets are ones which are finite and infinite. Okay, or finite or cofinite. On the other hand, which ones satisfy the assumptions of this lemma? Which subsets of this structure are invariant under automorphisms?
Any subset.
Yeah. I think there's this rule that you're not allowed to say any in mathematics. Just, you're not allowed to use this word. because depending on the context, it means for some or all. But of course, you meant all subsets, yes? And the reason is that this structure has no automorphisms, except the identity automorphism. So every subset is in them. Okay, so this is not true in general. And well, in fact, it's an if and only if, but I would just prove this implication. So why is this lemma true? And it's a nice result, and it explains the significance of this assumption. So let me explain why this lemma is true. So who has not seen Ehrenfeucht-Frizer games? Spoiler duplicator games. Good. You're at least ashamed of that. Well, too bad. But don't worry, we'll only play a role, a local role. So the reason for this is the following. Let me make a claim. The following are equivalent for two tuples Let me take two tuples and consider the following four conditions, and they're all going to be equivalent. Number one, A, B. Well, maybe let me start with number 4. A, B are in the same orbit with respect to all automorphisms. So, which means that there is some automorphism which maps A to B. And item 1 is going to be that for all A, B satisfy the same formulas of first order logic. So there's going to be items 2 and 3, of course, but this gives us already the lemma. Why? Because it says that if you're in different orbits, okay, then there's a first order formula which explains this, okay? And since there's finitely many orbits, then, well, there's finitely many first order formulas which are needed, and that takes care of what we want. So this will prove the lemma. But why is it true? Well, it's true because of two in the intermediate conditions. I think this, why does the equivalence of 1 and 4 prove the lemma? It requires a little bit more attention, but maybe we do this during the exercise session. Then I essentially wave my hands, but it's, I mean, I guess you can kind of see that it's what we need. But but the interesting thing is why it's true. Okay? So the first item is for all R, this is a number, duplicator wins the Ehrenfeucht well, the R rounds on AP. Okay. If you don't know what this game is, then I just remind you that they pick elements and they have to be similar. The spoiler picks an element, duplicator has to pick a similar one, and they continue like this. And yeah, that was very helpful. this is the reason why people talk about Ehrenfeucht-Frizer games. Okay? So Ehrenfeucht-Frizer games were designed to make this equivalence true. So this is a classical theorem about Ehrenfeucht-Frizer game, which says that duplicator can win the k-round game, well, the r-round game, if and only if the formulas the two tuples satisfy the same formulas of quantifier depth r. That's just by design. Okay? So far nothing to do. Now here comes the third condition, and we'll explain it in a moment, but let me just first write it. It's like 2, but for omega rounds. So it says, well, there's no quantification now because it's just one round, but a lot of rounds. So it says that duplicator wins the omega round game on the two tuples. Now maybe is a good moment to explain what this omega round game is. You could probably guess it, but if you lied about saying that you know what Ehrenfeucht-Frizer game is, this will help you. Or if you said the truth and you're you. So what is this omega round game? Oh, and this completes the conditions, and I will later prove that they're equivalent. So here's how the game works. The omega round game. We start out with our tuples. So these are elements of the structure, these are elements of the structure. Now, spoiler comes, and he picks either here or here, and he picks an element. Say he picks below an element bien plus 1. Now duplicator comes in and responds with a matching element. And what does it mean that they're matching? It means that this and this satisfy the same quantifier-free formulas. Okay? So if duplicator failed to produce a matching element, which means that he produced something but it doesn't satisfy the same quantifier-free formulas, then he loses immediately. So duplicator is only going to be able to die immediately. So the only way he's going to win is to survive forever. Now spoiler looks at the situation and it chooses either this side or that side. For example, this time he chooses this side. He produces another element. And now duplicator has to respond with a matching element. If he doesn't, he loses. Otherwise, duplicator chooses another. This time he chooses the top side again. And duplicator has to respond. So this is just the Ehrenfeucht-Frizer game. Now if it would be say 10 rounds, then they would stop after 10 rounds. And then if duplicator managed to survive 10 rounds, he would win. But in the omega game, they just go on forever. So that's what the omega game, I mean, I guess the name says it all, okay? So now let's see what's obvious. So we now all know what everything is, what things are defined. Clearly, if you can win the omega round game, then you can win the 10 round game and the 12 round game. If you are in the same orbit, so there's an automorphism which maps this to this, this gives you a clear winning strategy. What do you do? If, say, spoiler plays this, then duplicator replies with the automorphic image. And he just replies with the automorphic image, either from top to bottom or bottom to top. And automorphism preserves all relations, so they would be similar. So this is clearly true. So what we need to discuss is we need to discuss the remaining two implications. And let me start with the second one, which is always true. So this is always true. Doesn't use the assumption on oligomorphism, while the assumption on oligomorphism is going to be used here. Okay? So maybe this is a useful piece of knowledge, namely isomorphism. The finite round games describe first order logic. The omega round game describes isomorphism. It's just a useful thing to remember. So which one do we do first? Well, let's say the correspondence between finite round games and isomorphism. And it's kind of obvious. Well, so suppose that you can win the omega round game. Why are they isomorphic? It's very easy. What do we do? We have our two tuples, the white ones, A and B, and we want to establish an isomorphism, okay? So spoiler plays as follows. He first plays some element here, okay? Duplicator responds with something. Then he plays some element here, it's a very generic strategy. Duplicator responds with something. Then he plays some element at the bottom, okay? So he just plays it on all sides. Like if in the previous round he played at the bottom, then the next round he plays at the top. Again, and duplicator keeps on responding, okay? So this is so far not very helpful. What is the specific choice of spoiler strategy? The only thing that he ensures is that all elements of the structure appear in the bottom row and all elements appear in the top row. That's what he does. So I just there is an assumption that A is countable. So spoiler strategy is in even numbered rounds he plays an element of the bottom row that has not been played so far, and in odd numbered rounds he plays an element of the top row that has not been played so far in the top row. Okay? So if spoiler uses this strategy and duplicators respond in some kind of way, the result is that all elements of the structure are seen in the top row and all elements of the structure are seen in the bottom row. And well, the thing is an isomorphism because that's it preserves the predicates because that's what the.
How do you know that if he chooses something which was not here before will cover all the elements of it?
Again, sorry?
So you cannot choose arbitrary elements of A to cover all elements of A, right?
I didn't understand this.
There are countable subsets of A which are not the whole A.
Yeah, so maybe I was not clear. So choose some enumeration of the structure. C1, C2, C3, and so on. So spoiler plays the following strategy. Suppose we have played n rounds. What he does is he plays in the where is my color? So if it's an odd numbered round, he goes for below, and essentially he plays Cn. If it has already been, he just plays it unconditionally, okay? And so duplicator responds with something, and he essentially ignores his response, and in the next round, he's going to play Cn again. Okay? So that's what spoiler does. And if he follows this strategy, you have all elements of the structure here, you have all elements of the structure here. There might be repetitions because duplicator's response might use something that was previously played. Okay. But you will see all elements of the structure here and all elements of the structure with possible repetitions. Now, if there is a repetition here, then the corresponding elements will also have a repetition because equal elements must be mapped to equal elements by a winning strategy. So this saved. So this explains this thing. That's a useful thing to know, that isomorphism is this infinite round game. And what about the last thing where we use oligomorphism? So here's the argument. Suppose that we have, say, played 3 rounds already, okay? And I'm spoiler now, okay? And
what's the isomorphism like?
The isomorphism is I look at, well, Cn was played here, then it's mapped to whatever is above it. That's a function. So the isomorphism is defined as follows. I look at the bottom row, and I want to know what does the isomorphism do to some element C. So I look for C in the bottom row. I am bound to find it, because spoiler strategy would place C eventually in the bottom row. And then on the top row, I look where it's somewhere here, and duplicator responded with something like this, then it's C prime. Okay? And now I would have to justify that, first of all, it's a function, which means that if C appears several times, then it's going to be the same C prime on top. But this is true because in an Ehrenfeucht-Frizer game, you cannot map something to C prime and then to something else, because that would, this would violate the condition of an Ehrenfeucht-Frizer game, because here you have the quantifier-free formula which says that this is equals to this, and here it would be violated. So it's a function, and for the same reason it preserves all relations in the vocabulary. So it's an isomorphism. Okay. So now let's analyze, let's continue with this implication.
Excuse me?
Yes?
Could you please read the second point?
The second point says, for every... Does this solve your question?
Yes, but could you still...
I'll still read. So it says, for every quantifier rank, 0, 1, 2, etc., duplicator wins the Ehrenfeucht-Frizer game of R rounds if the starting configuration says that the tuple A is on top and the tuple B is on bottom. And please feel free to do this kind of thing, because, yeah. So now I want to prove the last implication. So how does it work? Suppose we have, the game has reached this situation so far. So we started out with the white things and we've played 3 rounds, okay? And now I'm spoiler, okay? Now, what is my color? And I'm thinking, you know, what should I play now? Is this the color? And I'm thinking maybe I should play B here. And then I'm thinking, no, maybe I should play B prime. And I'm wondering which one would be the better move, okay? But now imagine that B can be mapped to B prime by some automorphism which preserves all of this. Okay, so pi does not move any of these things. So pi makes A1 to A1, B1 to B1, Bn plus 1 to B. Okay, so it's so I can move B to B prime with an automorphism without moving any of this. Okay? Is it clear that if I can win with B, then I can also win with B prime? Whatever would happen if I have a winning strategy with B, then I apply pi to this winning strategy, and then I will get a winning strategy for B prime. Okay? So if I, as spoiler, I'm hesitating between 2 possible moves which are in the same orbit with respect to automorphism that preserve the state of the game so far, it doesn't matter which one I choose. Okay? Now, by oligomorphism, and here I'm using this assumption on oligomorphism, there's finitely many things I could do. Because there's finitely many atoms up to automorphisms which preserve this. We've proved this previously. So by definition, there's finitely many atoms up to automorphism which don't preserve anything. But then we proved last time that if I restrict automorphisms to, you know, fix something, then there's still finitely many cases. Which means that if I just restrict my moves as spoiler, so I could maybe do some moves as spoiler here and some moves as spoiler here. If I just choose one possible move for every automorphism type, then by restricting myself as spoiler, this will not make me, I can still win if I could still win. Okay? But the same argument applies to duplicator. So now it's duplicator's turn. And then he might ask, well, spoiler played this, so I could play this or that or that. Again, if he considers, if he's hesitating between 2 choices which are in the same orbit with respect to the history of the game so far, then it doesn't matter which one he chooses. So he has, up to these orbits, he has finitely many choices. Okay? So what that means is that if I consider a restricted version of the game, where I'm only allowed to use 1 move per automorphism type, then this game has the same winner. Whoever wins this game wins the old game. So it's a new game with finite degree. So if we consider this restricted game, So to be a little bit more formal, in the restricted game, whenever I get to have a choice, I'm only allowed to use the first atom, the first possible atom with respect to some order on the structure, up to automorphisms of the history of the game so far. This is the restricted game. Has finite branching. Okay. So what is this restricted game? You can think of, it's a graph. Well, it's a tree. Finitely branching tree. And the game is as follows. In even numbered positions, spoiler chooses a child. In odd numbered positions, duplicator chooses a child. Okay? And once in a while, duplicator gets blocked. So here, spoiler wins immediately. But sometimes the game continues forever. So it might have. And okay? Now, consider a game which is finitely branching. Then here, what this duplicator wants to do is he wants to live forever. Okay? But in a finitely branching game, you can live forever if and only if you can live for arbitrarily long. Okay? So, if duplicator has a strategy to survive one round, if duplicator, so in a finitely, let me write it here, in a finitely branching game, duplicator can survive forever if and only if for all R duplicator can survive our rounds. And this is relatively easy. It's essentially the Kenning lemma. There's nothing going on here. So if you can live for arbitrarily long in a finitely branching game, this is very important, then you can live forever. Therefore, since the restricted game is a finitely branching game, it follows that conditions 2 and 3 are equivalent, which finishes the proof. Okay?
So I have a question. So, like, when we have made this move in order to restrict the game, we make this assumption that, like, we choose an automorphism, like to choose one of the possible atoms, right? And we said that the automorphism doesn't touch the history. But I mean, cannot it basically potentially break something into the future? So then the strategy changes kind of in the future because the automorphism.
Well, the answer is no, it cannot. But you're right, this requires some justification, yes? So you would have to formalize this a little bit. So you say, imagine an automorphism, so let's come back. But it's a legitimate question, but it has an answer, which is no. So let's come back to that question. So suppose that I have two choices of things that I could do as player spoiler, B and B prime, and B and pi of B, where pi, history, is history. And this is the history. Yes? So this is the situation that we're discussing. Now what I claim is that spoiler wins with this move, has a winning strategy with this move, if and only if spoiler has a winning strategy with this move. So to prove this, one has to discuss the question that you're doing. So what you have to, but it's just unfolding the definitions, because then you just say, take some, what does this mean? Suppose that spoiler has a winning strategy here. This is a strategy. So now one has to remember what is a strategy. It's a function from the history to what the play is. And then essentially what you do is there's really nothing surprising happening. There's a natural way, if you have one strategy, to map it to another strategy using pi. And then if you just unfold the definitions, you will realize that this strategy is also a good strategy. And what that really means is that this is a strategy for spoiler, so you just have to check what happened. Does it win against any strategy of the opponent, which is duplicator? So you just say, well, here comes duplicator with his strategy. So what you do is you just take pi minus 1 of D. It's another strategy. And then, well, he wins against that one, and then this follows that he wins against this one. So it's just unfolding the definitions, but what goes on inside, I really haven't answered your question in the intuitive level, but in the formal sense. But if you think about what all of this means, this really takes into account the fact that, here you discuss future things. Okay? Okay, so this completes this theorem. And this is quite an important result, because it says that in an oligomorphic structure, any automorphism closed property is definable in first order logic, and this will be extremely useful. So, let me erase this. Once you get this result, you get this. It's just some symbol pushing, but essentially the fundamental thing is that you can rewrite isomorphism closed properties into first order formulas, and once you do that, you can change these things into syntax. So that's the theorem. So it says for oligomorphic structures, these two notions are equivalent. And now let's do an application of this result. We already had one application, which was graph reachability. Let me give you another one, which is automaton minimization. It will be the same idea as for graph reachability, but since it's a different example, and essentially what I want to do, I want to do the example for graph reachability a second time, but you would say, well, you shouldn't do the same things 2 times, so I'll just do it with a different problem, but it's the exact same reasoning that happens. Okay, so consider the following problem. We fix a oligomorphic, and with
another question, like we did an assumption that A is countable at some point.
this is all the time actually. So yeah. I discuss countable structures all the time. And let me explain, I mean, apart from making this theorem true, there's other reasons why I discuss such structures, and it will be actually visible here. So what does this mean? This can be understood in 2 different ways, and I use the one which is non-standard. So what I mean is that okay, so this still doesn't answer the 2 variants. Decidable first order theory means that you can input a formula and say whether or not it's true. But the formulas that I will talk about is can use constants from A. So this is what I mean by first order formula. So let me just explain why this is important. A classical example of a structure with a decidable first order theory in the usual sense, but not in this sense, is the real numbers with addition and multiplication, 0, 1. The field of real numbers. Tarski's famous theorem tells you that if you're given a first order formula, well, without constants, because it's not even clear how you can write them down, then you can decide whether or not it's true. Okay? But for my purposes, I want to allow formulas which can use 3, because I'm allowed to write 3 in my set builder expressions. Okay? So so in order for this to even make sense, it needs to be countable, because there needs to be a way to represent the elements of the structure. Okay? So I work with structures which are countable and are decidable. And now, let me give my example, and it's as follows. So I want the following decision problem. Input, it's automaton minimization. I'm given a deterministic finite automaton. By set builder expression. So This is a set builder expression, this is a set builder expression, and so on. Given by a set builder expression. And the output is the minimal automata. So you might even ask, well, what does that even mean? But, well, you will see from the algorithm what that means, okay? And it exists in particular, okay? And it's the. That's, which means there's just one, okay? So let me just do the algorithm. And the algorithm works, it's the stupidest algorithm you could imagine. It's the usual, I think it's called the Moore algorithm. Okay, so I start off with, generally speaking, I will consider my target thing is to consider states which are equivalent in the sense that they accept the same words. And I will start off with an over approximation of this equivalence, and it's going to be two states are equivalent, so this is supposed to be an equivalence relation. Okay? Two states are equivalent if, well, these are in Q squared, and it's just that. I write this out in symbols not only to bore you, but to see that this looks like a set builder expression. Yeah, it's not really a set builder expression, because in set builder expression the things you're allowed to write here are only atoms. Okay, and here what I put is states. But I hope that you can believe me that if you're given a set builder expression for this thing, then you can quickly come up with a set builder expression for this. It's not literally this, but it looks kind of similar. So, a set builder expression. So we can come up with a set builder expression for the initial equivalence relation. It's just all accepting states are in one group and all non-accepting states are in the second group. Okay? And then you just do the usual thing. In the next step, you consider, you refine your equivalence by saying that, well, by saying this. They have to be equivalent in the previous step, and furthermore, every single step of the automaton takes you to equivalent states. So, for all A in sigma delta of PA delta of QA is in EN. Again, it looks like a set builder expression. It's not literally a set builder expression in this sense, because these are allowed to quantify over just atoms and not elements of set builder expressions. But this is not a big deal, and if you just do some symbol pushing, you can figure out that you can easily compute a set builder expression for this. Okay? So what we get is equivalence relations, which are finer and finer. I never liked to do it this way, but what does inclusion on equivalence relation means? It means finer. It means fewer things are equivalent, so the equivalence classes become smaller. Okay? They keep on refining. And, well, I claim that this must reach a fixed point. So it must stop refining at some point. And for this, I will use that theorem. Okay? And so far, I have just used set builder expressions. There was no need for oligomorphism. And now, we switch from the syntactic perspective, which is the perspective of set builder expressions, to the semantic perspective, which is the perspective of orbits. So what is it? Well, what is En? It's a subset, it's a set of pairs. Yes? So here's a simple thing. If A supports the automaton. So take some tuple of atoms which supports the whole automaton. Or let me to do a special case, it will be maybe simpler to see it that way. If A is equivariant, which means supported by the empty tuple, which means that if I apply any automorphism of the atoms to Q, I get Q again. If I apply any automorphism of the atoms to sigma, I get sigma again, and the same is true for all things. Then the observation is as follows. Then also E0, E1, all of these are equivariant. Yes?
So if A is equivariant, this means essentially that it's an orbit?
A union of orbits.
A union of orbits, okay.
I use the term, maybe just some vocabulary, I say sometimes A orbit. This is an orbit with respect to automorphism that preserves this, and I use the word equivariant orbit. For the biggest possible orbits, namely when this is just all automorphism. So this is the same thing as an empty tuple orbit. And sometimes I just say orbit, and that would mean this, okay? So being equivariant means it's a union of finitely many, of orbits, but because it's orbit finite, it's going to be of finitely many orbits, okay? So now this is a statement which says that if the whole automaton, so not the states, the alphabet, the transition function, it's invariant with respect to automorphism, then the same will be true for this and this. I hope this is completely natural, yeah? It's a property that's preserved under all sorts of natural constructions, okay? So this is relatively easy to see. I mean, it's a two-line proof, but I want to. What does that mean? Well, let's draw a picture. This is Q squared. Okay. It's a set of pairs. Now, orbit finite sets are closed under products. I don't remember if we proved it, but it's true. Okay? So it's an orbit finite set, which means it has finitely many orbits. So these are the orbits, equivariant orbits in this case, because it's an equivariant set. But if it was if it was supported by 1, 2, 3, then I would talk about the 1, 2, 3 orbits, and the same argument would apply. So I partition Q squared into the orbits. I don't know why I draw bricks. That looks kind of cool. So that's the only reason. So it has finitely many orbits. These are the orbits. Which means that, what does this mean? It means that if I take an element here and I take an element here, what's an element here? It's a pair PQ. Yes? And I take some other element, P prime, Q prime. This means that they're in the same orbit, which means there's an automorphism which maps P to P prime, and the same automorphism maps Q to Q prime. Okay, that's what it means. Now, this observation here says that if you look at En, it's a subset of Q squared. Yes? But it says it's equivariant, which means that if I have one pair in En and I have a same orbit pair, then it's also in En. What that means is that En, the partition into En, is coarser than the partition into orbits. It just means that every En is a subset of these things. So I have something like this. Now, this explains why this cannot go down forever. Because it gets maybe, at some point it will hit the bricks. Okay? You cannot go beyond that. Okay? So this algorithm will stop in at most as much time as Q squared has orbits. In particular, in some finite time, you will reach an equivalence relation that will not refine anymore. And that means that this classical Moore algorithm for partition refinement, if we're working with automata that are set builder expressions and our atoms are oligomorphic, so this thing holds, then the classic Moore algorithm will necessarily stop infinitely many rounds. This is not true for atoms which are not oligomorphic. Okay? And now, so we have used the semantic perspective here to prove termination. Then now once we have done that, we can come back to the syntactic perspective. And then we can say the new set of states is the quotient of the old set of states with respect to this equivalence relation. So let me just write it out. So you take for every state in the old one, you take its equivalence class. I just literally wrote out the quotient, yes? But I did it so that you can see that the quotient is also a set builder expression. Again, this is not literally a set builder expression, but you can, starting out from the way it's written, you can put it into an actual set builder expression, okay? So the quotient is a set builder expression. So set builder expressions have all sorts of nice properties that are closed under products, you know, under these one-step successors, closed under quotienting with respect to things that are set builder expressions, etc. But the semantic property is used to assure termination. And then once you've done this, then you can, well, you can do the other things quite easily. So we end up with constructing a set builder expression that represents the minimal automaton. Well, I should justify that it's a minimal automaton, but it's kind of easy to see that if you take two states are equivalent with respect to this stabilized equivalence relation if they accept the same words, and that means that they're a good choice for states of the minimal automaton. Okay? So this is an example of what you gain from having a set builder expressions. You can work with your objects, you can manipulate them, pair them, quotient under them, apply functions to them. But from the fact that there's finitely many orbits, you can prove termination results. Okay? How fast does it terminate is a different story, and I will not have any time in this lecture to do this, but let me just maybe say it in a few short words what happens. Well, in general, it takes exponential time. Everything takes exponential time. But if you take the perspective of say, fixed parameter tractability, then there is a good parameter which is one to investigate, namely, it's called the dimension. So here, this set here has dimension 2. And the reason is that at any given time I quantify over 2 atoms. Well, one would have to be a little bit more careful what that means, but this is sort of like 2-dimensional. And I can nest a 2-dimensional set inside a 2-dimensional set and so on, and it's still going to be 2-dimensional set. So it turns out that if you fix the dimension, then these constructions are polynomial time. So it's even not so bad in that sense. Okay. Let me maybe conclude the minimization with a nice example. Well, you be the judge if it's a nice example. How much time have I got? Okay, good. No, the example is a good thing for the exercise session. So we'll try to minimize an automaton and see what happens there. Similar things that you can get using this type of argument is that you can do, well, a lot of, say, all fixed point algorithms can be solved this way. Examples of fixed point algorithms are emptiness for context-free grammars, well, graph reachability, but there are algorithms which are not fixed point algorithms, and for example, testing isomorphism between 2 graphs is not a fixed point algorithm. In particular, well, if it would be, known to be in polynomial time. So these will not necessarily work, and as I mentioned in the last exercise session, isomorphism question for, you're given two graphs given by set builder expressions, and is there an isomorphism between them? This is not known to be decidable, and it seems, I think the evidence is that it will be decidable, but that would require quite a lot of work. Yes?
So the minimal automaton is kind of defined by this algorithm? Because like, what makes this automaton minimal? We see that we have kind of reduced, but what was the point? Like, can we, for example, argue how much smaller it is or something like this?
Well, definitely smaller.
Or equal if it was...
Yes, but there's a principled answer to this, which is as follows. There's a natural thing called a homomorphism of automata. And then the minimal automaton is something that is reached from your original automaton by a homomorphism, because, well, it's a quotient. But it's called the minimal automaton because it has the property that it doesn't depend on the automaton you started with. So if you start out with a different automaton, as long as it recognizes the same languages, you reach the same automaton. It's a canonical thing. And the fact that it's canonical, if you remember your proof from the automata, from your basic automata course, it gave you a construction of the minimal automaton, well, this one probably, and there was a proof that it does not depend on the starting automaton. That proof did not use at all the assumption that the state space was finite or the alphabet was finite. So it applies here as well. But what is gained here is that you show that this construction, it's computable, and that's not always true. Okay, so let's continue. So now we have seen the usefulness of oligomorphic structures, but where do you get oligomorphic structures? So I'd like to finish today's lecture by giving you a construction which allows you to create oligomorphic structures. And it will have the property that all oligomorphic structures which I know are a result of this construction. So at least it's maybe the only way to get them, at least. I mean, there are some artificially constructed oligomorphic structures which do not arise from this construction, but they are obtained by forcing to get counterexamples to things. So it's not very useful. So it will be, to make this a little bit simpler, I will assume that there's no functions. So in general, a structure is equipped with relations and functions. You can view a function as a special case of a relation, but the distinction between relations and functions does make a difference if you care about quantifier-free formulas, because and I will care about quantifier-free formulas in a moment. So functions make things a little bit more complicated, but if there's time, I will explain that. So let's just consider only relational structures, and I will give you a list of structures which are oligomorphic, but in fact have a stronger property. So one is this. Well, the one we have. So natural numbers with equality. Remember, it's really nothing here, but I just write equality because just to indicate that there's equality. Maybe I could put it like this. Equality is always assumed to be for free. So it's a universe equipped with no relations or no functions. And the fact that it's natural numbers is not important. It's just a countable set because these logical properties don't care about isomorphism. So it could be the integers or whatever. Yeah, it's just a countable set with no structure whatsoever. The rational numbers. Let's stop there for a moment. there was this random graph, which we'll get to in a moment. And one thing you can think about, what are the finite substructures of this? So I restrict the structure to a finite subset. What do I get? Sorry? Well, I get okay, maybe this question, I don't want to insult you by asking it. You get a finite structure with no relations. So I will look about the substructures. And here you get finite with no relations. Okay, nothing interesting. What do we get here? No, I'm asking about, I restrict it to finite structures. So what I get here is I get any finite total order. Yes? All of them. Well, I use the word any. All finite total orders. And what I will try to explain now is that this is the unique structure in a certain sense which gives you all finite total orders. So it's called the Frizer limit. Same Frizer. So it turns out that if you start out by saying I care about finite total orders, this is the unique infinite structure that corresponds to them. The integers with order will not be okay. And maybe let me give you another one, the random graph. So the random graph, I will explain it later. It's also known as kind of funny as the Rado graph because it was studied by Rado. Two synonyms in this case. And it's a graph. Well, the random graph definition is the following. I mean, we said it, but I said it once again. Imagine you have an countably infinite set of vertices. For each, suppose you want the symmetric random graph. It doesn't matter. There's also the directed random graph. But let's say we want the undirected random graph. So for each two vertices, you flip a coin. You put an edge or not, depending on the result of the coin. So you get a distribution on graphs. And then it turns out that up to isomorphism, there is one graph with probability 1. And this is the isomorphism type of that graph is called the random graph. So it's a kind of funny thing, but it turns out that it's the unique best graph. With the Frizer, well, what are the substructures of this graph? If you think about it, you can get any graph this way, yes? Because if you want to get, for example, a square without, if you want to get this, so you don't have these edges, then, you flip your coin for 4 vertices and you might get it. And if you don't, you try somewhere else, and eventually you're bound to get it. Yeah? So you get all undirected graphs. Finite graphs, yes. So the class of all undirected finite graphs has a limit, and has a Frizer limit. It's called the Rado graph, the random graph. But not everybody has a Frizer limit. So if you take all planar undirected finite graphs, then there is no limit. I mean, I haven't said what the limit is, but I think it would be good to start with these examples. Another thing that doesn't have a limit is you take, so a finite order, it's kind of the same thing as successor only, but it's not really the same thing. So let's call this class of paths all finite directed paths, well, paths. So these are structures of the form, these are directed graphs, which look like this. So it's not the same, well, it kind of corresponds to a total order, but I don't have the transitive closure, okay? And it turns out that this is a reasonable class of graphs, but it doesn't have a limit as well. So sometimes you have a limit, sometimes you don't have a limit, and it will turn out that when the limit does exist, it is going to be oligomorphic, okay? So now I explain what the limit is. So the notion is so I will introduce one more, well, there will be two more definitions that will appear. And the one that I will study now is going to be a homogeneous structure. It's a stronger property than oligomorphism, as I will explain in a moment, at least for relational without functions. If you have functions, it's a little bit more blurry, but without functions, as is the case here, it implies oligomorphism. So what does it mean? It's a very simple definition. A is homogeneous if you take any elements here I took 3 elements, but in general you can take more, but finitely many elements. And you take a partial automorphism. Which means you map this triple of elements to some other triple of elements such that they satisfy the same quantifier-free formulas. In other words, they satisfy the same relations. Okay, so it's a partial automorphism. So a partial finite automorphism is just a function from one tuple to another tuple. It could be there could be repetitions, so a B2 could be mapped to A3 or something. That's allowed, which has the property that the same relations are satisfied by the source as by the target. So for example, if there's an order relation and this guy is smaller than this guy, then this guy is smaller than this guy. Okay, that's a partial automorphism. And it says that if every partial finite automorphism extends to a total one. Full automorphism. Also known as automorphism. Okay? So that's what homogeneous means. If you can locally map this guy to that guy, then you can extend this to a global thing. Okay? So maybe before we work with this definition, let's consider some examples. It is indeed homogeneous. Think about it. What's a partial automorphism? So here's Q, and then you can map this guy to that guy. And if it's supposed to be a partial automorphism, you just have to be order preserving. Yes? And then you can extend this to a full automorphism. You can say a piecewise linear function if you want. But what about Z? It's not. Why? Because say you have -1, say 2, 7. I can map it to 2, 5. And this is a partial automorphism because the same order formulas are satisfied here as here because the quantifier is free. So 2 is smaller than 7, 2 is smaller than 5, one equality. So it is a partial automorphism, but it doesn't extend because, well, the gap here is bigger than the gap here. So this is not homogeneous. It's also not oligomorphic, and it's not a coincidence. Okay? Because it's going to be essentially, well, for finite vocabularies, it's going to be more or less the same thing. Okay? Let's take, well, here it's clearly homogeneous. You map 3 elements to some other 3 elements, and you can extend it to a permutation. With the random graph, it's a little bit more annoying, but it's true. Okay, maybe this is, let me give you maybe, okay, that would be enough for now with respect to examples. And now I can explain the Frizer limit. So the Frizer limit of a class of structures is any homogeneous countable structure which has these structures as its substructures exactly. Okay? So for example, if I want a homogeneous structure which has exactly the finite total orders, then as substructures, then 2 candidates would be this and that. There's other candidates as well. Both of them have all finite total orders as substructures, but this one's not homogeneous, so this is not going to be a good candidate. And it turns out that there is a unique Frizer limit. So let me write it now. This is the theorem. If it exists, it's unique. Not only is that, but we can understand quite well when does it exist. So I will write it here. Consider the function by structure that embeds into A, I just mean a substructure, but possibly up to isomorphism. So maybe let me draw a picture. So for example, if it's a graph, maybe a different color would be useful. The function which maps this is an embedding. So it's an injective function from one structure to the other, which such that if the same relations are here and as here. I draw it to underline 2 things. First of all, it's injective, so 1-to-1. But most importantly, it's not like a graph homomorphism. In a graph homomorphism, you have that if there's an edge here, then there's an edge here. Here, there's if and only if. Okay, so in the terms of graph terminology, it's an embedded induced subgraph. Okay, induced subgraph up to isomorphism, because it doesn't have to be inclusion; it can be isomorph. Okay. So consider the map which takes a structure and returns the things that embed into it. So it's induced substructures up to isomorphism, finite ones. So this is the map which goes here. And it turns out, what the theorem says is, there's a white. This is the Frizer theorem. Is a 1-to-1 correspondence between, on the one hand, it's countable homogeneous structures, up to isomorphism. Because I mean, if you replace A by an isomorphic structure, you get the same result. Okay? And classes of finite structures that are closed under what? Well, first of all, if you give all finite substructures, then it's going to be closed under substructures. Yes? And I mean up to isomorphic. So, substructure is not just contained, but up to isomorphism as usual. But that's not enough. And to amalgamation. I will explain this in a moment. So some classes are closed under amalgamation. This guy, this guy, this guy. Some are not, this guy and this guy. If you are closed under amalgamation, you can take, there's a homogeneous structure which gives you as all your substructures. Not only is that so, but it's a one-to-one correspondence. So if there's two candidates for your, there's two homogeneous structures which give you as your substructures, then they're going to be isomorphic. There's only one way to do it. So that's the theorem. Let me see how much time I've got.
What is an amalgamation?
Yeah, I haven't finished. So this is the only thing. So what is this property which ensures that you have that you come from a homogeneous structure? Well, you should look at homogeneous structures and then look at their substructures and what kind of properties will you have arising from homogeneity. Well, maybe it won't be completely clear, but I will give it to you. So what is it? So it's the following thing. So I have a class C. This is a class of structures. And what does it mean to be closed under amalgamation? It means that I take, let me just do it for the class of, say, graphs. Okay? The class of graphs, of finite undirected graphs, is closed under amalgamation. Okay? And why is it so? Because, well, I need to explain. So the picture is this. Imagine you have two graphs with a common part. Okay? So for example, the common part is going to be this. This is the common part. And I extend it in two different ways. So these are two embeddings. Well, I extend it, so it's going to be I guess you can sort of see where this is going. That planarity will play a role. So one way I extend it by adding this. Well, I cannot just add an edge, because if I just add an edge, it's not an embedding. Because here they were not connected and here they are connected. But I can cheat and I can just add an extra vertex and now it's an embedding. Okay? Here I can do the same thing. And such a thing is called an instance of amalgamation. Okay? And the amalgamation property says that every instance has a solution. And I guess you can imagine what a solution is. So who doesn't see what a solution is going to be? Oh, wow, nah, you're just being too modest. A solution is something that joins these things together. Okay? So a solution would be, so here I give you an example of a solution, which might not always exist because everything has to be in the class. A solution is a new graph, in this case, a new object in the class. So it needs to have this. And, well, such that the things commute. So so here's an example of a solution for this particular instance. I can add this and this. It's a graph which extends this, and in a way that's consistent with their joint part. Okay?
But you can glue these two red vertices together.
I know. It was meant to be my final word. It was meant to be my punchline. But so the way I drew this picture, well, I hope that this picture, so let me just, this is a solution. So a class is closed under amalgamation if it has this property, which means I take 3 structures from the class, I embed the first one into the other 2, and for every way of doing this, there has to be a 4th structure in the class and a way of putting them together. Okay? And all of the arrows are supposed to be embeddings. Okay?
So for all possible kind of moves H1 and H2, this is something.
Yes. So the property is that well, for every instance exists a solution. Okay? And everything has to be in the class, so the amalgamated thing has to be in the class. Graphs clearly, if you think about this, well, up to isomorphism, you can just think that this is 2 graphs which have an intersect over some common subgraph, yes? And then, well, I just explained, and the sort of union across this common intersection is the amalgamation. So undirected graphs have this property, well, graphs without edges have this property, total orders have this property, we can figure out during the exercise session. And as I wrote, planar graphs don't have this property. And now you stole my punchline, because this sort of looks like a counterexample to amalgamation for planar graphs. But this is not. There is a counterexample, but it's not this one. Because here you can amalgamate it in a different way. This is also an amalgamation. Namely, there's nobody saying that these 2 points cannot be the same one. That's and if you do that, then this particular instance of amalgamation in planar graphs happens to have a solution in planar graphs named this. But then if you do put some gadgets in some places, you will be disallowed to do that, and then the result, you would get a counterexample of amalgamation for planar graphs. So it does not have amalgamation. We'll do this one in the exercise session. So what does the Frizer theorem say? The Frizer theorem says that if you have a class of finite structures which has this property, then it will arise from some countable homogeneous structure. And in fact, a unique one up to isomorphism. That's why we can talk about the Frizer limit. I will not prove the Frizer theorem. It's the type of thing that you can figure out on your own. I mean, it might take an hour or 2 or 3, but it won't take 10 years. Okay? Maybe let me now just finish. I mean, I will be a little bit over time, but please forgive me. Why is it oligomorphic? Why does this imply? And this is a one-liner. So tell me, up to finite automorphisms, up to finite partial automorphisms, how many triples can I have? Well, a triple is just determined by which relations are satisfied by it. If I assume that there is a finite vocabulary, so here it should say unfinite vocabulary. So if you have finitely many relations, if it's for example, if there's one binary relation, the partial automorphism type of this is just determined by which edges hold and which edges don't hold. There's finitely many ways you can do this. And so if the edges hold here in the same way, then they're the same up to partial automorphism. by definition of homogeneity, they're the same up to total automorphism. So the number of orbits of k tuples is at most, and in fact exactly, the number just of quantifier-free types that you can have, and there's finitely many of those. Okay, so this implies oligomorphism, and the same argument actually shows something more, and this is the last thing I want to say. If you remember, we showed that in oligomorphic structures, every orbit can be defined by a quantifier, by a first-order formula. So any property invariant under automorphism is going to be definable by a formula of first-order logic. For homogeneous structures, a stronger statement is true. Namely, quantifier-free formulas are enough. And this also is a one-liner, because if I want to determine the orbit of this triple, A1, A2, A3, all I have to say is which relations hold and which relations don't hold. And that tells me the orbit of that thing. And there's nothing more you can store about a tuple than the orbit. And the orbit is just defined by a quantifier-free formula. So homogeneous structures are even stronger than oligomorphic. Not only are they oligomorphic, but logic, not only does everything collapse to first-order logic, but it even collapses to quantifier-free formulas. So I'm sorry for extending, and let's have a break now. Thank you. Unless there's questions, yeah? Well, not let's have a break now. Jest dobrze teraz?
Tak.
Okay,
Ale echo jest strasznie.
strasznie.
Echo jest. A to nie jest po prostu, że słyszysz zarówno Mikołaja, jak i jego słuchawek.
Elektro Mikołaja.
No właśnie tak ze 3 razy. 3 razy.
A ten sam problem był przy wykładzie?
No. Może nie jest tak źle.
A, właśnie. Wystarczy wiele razy spytać i w końcu usłyszycie to, co się chciało.
Powiedz jeszcze coś?
To raz, dwa, trzy. Raz, dwa, trzy.
Okej.
Ja tylko raz powiedziałem raz, dwa, trzy. Okay. So, I think since we have the Frizer things on the blackboard, we can start by discussing those, and then we'll move backward. So, the class of paths, in this sense. Why doesn't it have a Frizer limit? Well, because it has to violate this. Why does it violate it? I want 2 answers. First a stupid one and then a slightly smarter one. So you have to start with the stupid one. And you have to guess what I mean by stupid one.
One is such that you got points and you in one way link into one in the middle and the other one in with 2 in the middle. But it's probably the smart one.
That's a smart one. So try to come up with the stupid one.
This one maybe the same number in both.
Okay, maybe I'll give you the stupid one. The stupid one is that, okay, let's start with the smart one and work down to the stupid one. You can have paths of different length. This is what Victor said. And you cannot amalgamate them. Okay? This is not an actual answer. And the reason is that this is not a path. That's a stupid thing. Because, I mean, in order for this, it has to be closed under substructures. We implicitly assume this anyway. So what you really, in order to potentially make sense, this would have to be finite paths and their substructures. So if you start with a path, then you can have 2 isolated nodes because you can just take some longer path and take the 2 endpoints, okay? So the class of finite paths, it violates item 1, but then if you just make item 1 true by saying finite paths and their substructures, then it starts to violate item 2. And this is the example, okay? I'm not sure if we want to do planar graphs now. Yeah, no. I don't want to do planar graphs. Let's do total orders. It's really nothing to do. I will not draw all the arrows, but just say the elements are like this, and there's all the arrows, you know, it's a total order, and I don't know. I amalgamate this into some total order which has two elements here, and this is one embedding, and then I have another embedding which uses, I don't know, triangles. Oh, they're not triangles, I think. Then how can you put them together? I mean, in more than one way, yeah? That's maybe all there is to say. So you can just, I don't know, you can start with the, maybe you can go like this. And here you could take any shuffle of the circles and the little, what's this? Rhombus?
Diamond.
Diamond, thank you. That doesn't sound so pompatic. So you can arrange the circles and diamonds and put them together in many ways. Yes?
Does any class of graphs defined by excluded minor can have a Frizer limit?
Well, some do, some don't. So,
can you give an example?
you mean exclusive? Well, excluded minor in the Robinson-Seymour sense?
Yeah. So the
Well,
fact class is closed by the minor.
I guess you mean something like non-trivial class or something,
Yeah.
because
All graphs are.
or graphs. Okay. Well, total orders have an excluded minor.
Yeah, because they are minor closed.
Yeah. So no, I think it's orthogonal to that.
And on directed graphs of that, maybe it's.
No, I'm sure it's.
You can then call.
I'm sure there's no connection between the two concepts. What people do consider is Frizer classes, which are defined not by excluded minors, but by excluded induced subgraphs, which also means that which are defined by formulas of the form like this. So say all triples of vertices satisfy blah blah blah, and this ends up just being that there's some forbidden patterns. So it's an excluded induced subgraph. And then so there are many Frizer classes are defined like this, including, well, not the planar ones, because there's some connectivity involved to define planarity, and that will not be of this shape. But the other things have this type. And an advantage of such a Frizer class, so many Frizer classes are like this, and then they have extra properties which arise from that. Yeah? And then you can even consider a decision problem which inputs a Frizer class, where the Frizer class is given by this and then does something. And so there are results like this. The Bodirsky people do this type of thing. Okay, let's continue. So here's a nice example. Well, you guys be the judges. But trees. What's my favorite example? So, no, well, I don't know if it's my favorite example. But so the class of total orders has a Frizer limit. So what about the class of trees? And the first thing is that this is an ill-posed question, because I would have to say what I mean by a tree as a relational structure. Okay? And there are several ways to do it, and they give different results. Okay? So let's try it out. So how would, well, the general idea is that this is a tree is like this, yes? So how would we model a tree as a relational structure? There's at least 3 ways to do it, and the least natural one is the one that's correct. So let's start with one way is to just view it as a directed graph. Yeah? That's maybe the most natural way. And this is going to be wrong for the same reason as paths. Yeah. Then you can turn it into forests, and then it's so that's not going to work. So if you take directed forests, say directed away from the root, then the same problem as paths arises. Well, because it covers paths, and paths cannot be. You cannot amalgamate paths even if your target structure is a tree. Okay, so that's wrong. What other way could you imagine? Well, this is the second natural way, which is clearly much better. So you view a tree as an order, or otherwise, and because of these substructures, it's typically going to be forests. Okay. So it's a forest. Forests with a descendant relation. So this can be axiomatized as orders, where for every node, this is the order theoretic formulation of trees. It's an order where if you take any element, the set of the smaller ones is totally ordered. But trees with forests with descendant relation, that's fine, good enough. Okay. Why is this closed under amalgamation or not? You know probably the answer anyway, so shut up. And yeah, be careful. If you know the answer, you get to be insulted. So go on.
If I take 2 vertices and in first way I connect the first 2, and then to the third one, and the second I would take second and the third connect them, and then
So you can imagine this tree and this tree. And you can view them as sharing these 3 nodes. So this is an embedding and this is an embedding. They preserved that this is an embedding. But you can't put them together. Okay? So no. What else can you do? How else would you model trees as a structure?
Wouldn't it be enough if just one starting vertex? Can we just start
Enough for the counterexample?
Yeah.
So
just with the 2, if we start with the 2, then take those embeddings.
no, I don't think that would be enough. So is this the question?
Yeah.
I mean, I guess it's this, these are isomorphic trees.
Okay.
Well, yeah, because these are trees where there's no order on the children, yes?
So can you explain one more time how this was, for example?
Okay, so I claim that this is an instance of amalgamation, well, with H1 and H2 being defined in the natural way, which has no solution. Okay?
And because of this,
Therefore, they are not closed under amalgamation. So this is a counterexample to being closed under amalgamation. So trees, if you view them as descendant orders, are not closed under amalgamation because we're forests.
So definition of being closed under amalgamation is that there exists solution?
For every instance.
Okay.
That's just by definition.
Excuse me, and in amalgamation, those embeddings, the atoms here are distinguishable, right? Like you label them in this example. And
No. Well, the picture is confusing. So what I meant, the structures we're working with are just forests. And then H1 is defined to be this embedding. And H2 is defined to be the similar embedding. So the numbers 1, 2, 3 were not part of the structure. They were just used to explain the embeddings H1 and H2. Okay, so it's this picture. I don't know why I did curly lines.
Okay, but still we need some way of distinguishing those elements because otherwise those two trees are isomorphic, right?
Well, not in a way that would respect this.
Okay.
So let's, because if you follow this, okay, if you have some potential solution, okay, it will have elements corresponding to this. Right? It will have elements like this, which...
So for the potential solution, we need to define two more embeddings, right? Going from the
Yes.
three on the left and going from...
So a potential solution would have embeddings F1 and F2. That's a hypothetical solution which does not exist. But this requires an argument, which we're doing now. So this hypothetical solution would be some forest with descendants and two embeddings of this guy and of this guy. But, I mean, it's not, maybe I just write it, it's supposed to mean that H1 followed with F1 is the same thing as H2 followed with F2. Yes? That this is a condition of being a solution. So that would mean that this element, if I followed it here, it would go somewhere. But if I followed it through here, it would go to the same place. Okay? So, and likewise, this guy and this guy. So these three elements are the targets of this with respect to H1 followed by F1, equivalently H2 followed by F2. Okay?
So it ends up in the same place, it means that it is the same atom.
It is the same element, yes.
If we are in Z and at the top we are 0, then on the bottom we are still 0, right?
No, all of these three blackboards are atom free. This is not about sets with atoms. This is just, there's no atoms, okay? So these are just normal graphs, vertices, and so on. The purpose of this construction is to construct a structure A which can later be used as atoms. But it is constructed without, in usual sets. Okay, so this is just... so let me try, I mean, let me just try to justify in slightly more rigor why this instance has no solution. If we look at this hypothetical tree, okay, then first of all it needs to be connected. These three nodes need to be connected because they are the image of a connected something in two ways, okay? And then you just have to ask, in a tree there's three possible shapes, like this, and the other one. Well, and all of them are going to be wrong. You couldn't use this shape because this is not an embedding. Yeah, because
So this edge is missing, right?
When I said they are like this means that there is no node where this guy couldn't be mapped to anybody here. Yes, because
It should be an
when I mean, this is supposed to be the closest common ancestor, okay? This is what I mean by this picture. Sorry, I interrupted you.
I was talking with you basically said what I wanted to say.
Oh, yes. And then you just figure out that all of these things are, but maybe let me try to explain. These trees look like they're isomorphic, but they're not isomorphic in a way which preserves these green lines. Well, what's the color? Is this green? They're not isomorphic in a way which preserves these green lines, because these green lines require this guy to be mapped to this guy to be mapped to this guy, and this guy to be mapped to this guy. And that's not going to happen.
I think it's a minor thing that actually the solution doesn't have to be connected, because you can...
This part of the solution. I said that these three are interconnected.
Yeah, sure.
The entire solution might have rubbish. Okay? Okay, so that doesn't work. So what can we do with trees then?
Maybe you can try the lowest common ancestor relation of two different.
This is a three-argument relation, yes?
Yes.
This is almost correct, but it's still wrong. So the idea is you have a, well, I use the word closest common ancestor. I try to because some people use lowest and some people use highest depending on how they draw trees, and you can imagine this leads to confusion. I hope this is more. Sorry?
Who draws trees with the root at the bottom? Do you know that people?
Yeah, well, I was like this. You know, you start out like this, if you can imagine. I mean, maybe you forgot, but at some point, at least when you were 5, you did that. So there must have been a moment when you changed. I changed quite late. I changed. Sorry?
I didn't name the ancestor. No.
Yeah, I changed when I was like 20 years old or something. I had to burn all my pictures and do them. And okay.
And common ancestor.
But there's many common ancestor.
Yeah, the relation on 3 arguments.
Oh, you want this relation?
Yeah, maybe. I don't know why, but you said that the previous one was wrong. So.
This is going in the wrong direction. So let's start with this. It's a 3-argument relation, which says this guy is the closest argument relation. So why is there a problem? Well, it's the same exact thing. Well, the previous function continues to be an embedding. Because as a relational structure, nobody is a closest common ancestor of anybody. And this continues to be true in this substructure here. And making it common ancestor wouldn't fix the problem as well. So, but if you think of it as a function, which I forbid at some point here. And now is a good time to revisit that, because functions can be a bit useful, okay? So now let's adapt this stuff a little bit. And let's discuss classes with, you could do it, by the way, with a relation, which would be a 3-place, there would be a 3-place relation which says it's like this. Another 3-place relation which says like this. And there's the other one when they're like, and you, well, yeah, and that would work out from what I remember. But the functional solution is nicer, and it allows us to discuss some other things. So let's go for the.
So you say it would work with a relationship saying that, oh, like the 2 guys on the left have a common ancestor, which is different than the one on the right.
So you would have a relation like this. This is the name of the relation. And, well, the semantics kind of follow from the name. And then you would have 2 others with similar shape, and, well, you wouldn't need the other one because you can just rearrange x, y, z. But you would probably need this one. And maybe even this one you might not need, because this guy already gives you Well, as long as you have ancestor, probably if you have 3 independent nodes and they don't satisfy this nor any of its permutations, then they necessarily must satisfy this.
Or they are not connected.
Yes, correct. So you're right. Yeah. So you just add such relations, and it would. So if you add enough relations, it starts to become closed under amalgamation. It's not a very elegant solution. A more elegant one is to add a closest common ancestor function. Well, yeah. Which maps 2 nodes into their closest common ancestor. That changes several things. So first of all, now when we talk about substructures, you can't just take a subset of the universe and restrict to it. It needs to be closed under the functions. Okay? So that's what a substructure means, yes? Well, actually, this definition of embedded substructure it continues to be true without changes, because if you have an embedding, then the thing you're embedding is by definition closed under function. So there's actually no need for that. But just remember, if you have only relations and you have a big structure, and you take, say, 3 elements, then you can just restrict it to those 3 elements and it's fine. Now what you need to do is you need to take all things which are generated by it using the function. Okay, so that's what I mean by a substructure in the presence of functions. So it's now the role is going to be, now let me just make the changes. It's going to be finitely generated. Okay, and likewise here. And that's it. The theorem continues to be true. Okay? And since I did not prove it, it makes life easy because I don't need to reprove it. Maybe a little bit of explanation. What a homogeneous structure in the presence of functions is the same definition, but again I need to take a partial automorphism now. It needs to be an automorphism not between finite subsets, but finitely generated. This is finitely generated. So this is what a homogeneous structure in the presence of functions means. Okay? Now, and once you adjust the definition of homogeneous structure and the Frizer theorem, it continues to be true. So it's, that's all you need to do for functions. And now, let's discuss trees again with a closest common ancestor function. So first of all, there's a nice thing, which is that you no longer need to have forests, because if you, it's okay to have trees, because by substructures they need to be closed under ancestors, and then they will give you a root. Okay, so this is there's nothing. I mean, maybe it's not going to work, but it's but it will work. So it's potentially possible, and it will actually happen that you don't need forests but trees. So consider the class of trees. With a closest common ancestor function. You don't need the descendant now, because so the descendant is sort of an but we can think of the descendant anyway. So now let's try to check if this has amalgamation. And now it's trees, not forests.
But so like the substructure things is not broken now, the condition of the substructure. So it's closed on the substructure because it has to be generated, finitely generated.
Well, here it's not, well, a substructure of a finitely generated substructure is finitely generated anyway. So take this class and, well, okay, let's first check that it's true under substructures. Okay? So what we start with a tree. with a closest common ancestor function. So the universe is these nodes, and then there's this closest common ancestor. And let's try to get a substructure in the general sense. So what's a substructure? You start with some elements. Yeah. And then you, well, see what, if it was a relational structure, you would just restrict it to those elements and that's it. But now you have to take all things that are generated by these guys with respect to the functions. So what do you get? You get, well, this guy, because he's the closest common ancestor of these. You get, well, here you get nobody, but you also get this guy, because he's the closest common ancestor of him and him. In general, you don't need to get the root, because if you start it out like this, then your root might change. Yeah,
Oh, and you don't need to have all of the intermediate things.
no, you won't get this guy, yeah.
Okay.
Mm-hmm. So this is what's a substructure of a tree if you understand trees as in this way. And it's a very natural way of doing a subtree, yes? So you take the nodes and the things that are induced by them by the tree topology in where closest common ancestors. Okay, so it is closed, and now if you think about it, then the result is also a tree. I mean, you don't even have to think about it; it's clear, yes. So if you take a tree viewed in this way, so with a closest common ancestor function, you take some subnodes and generate whatever you get. You get a tree again. So it's closed under substructures. Check. Amalgamation. So this is just example. It's just going to be an example. So you take some tree. Okay? And then you embed it in two bigger trees. This is too big. And then you embed it into two bigger trees. I mean, what can they look like? I mean, it could be something like this one might have some nodes. Like this, and the other one will have some other things. Well, let's have a different shape, I guess. And now I want to put them together. It's kind of clear, yeah? So for example, you have this. I hope that's enough of an explanation. So you have to, these guys have to be the same node, and then you just have to put this and this together. And it's the same thing as with the orders. You just say, we assume that these guys are earlier and these guys are later, for your choice of understanding of earlier and later, yes? And likewise, so on paths, you have the added nodes on the left and you have the added nodes on the right, and you just put them in some order. First the added nodes from the left and then the added nodes on the right. If you have subtrees, then you can just put them in independent subtrees. And there's a natural way of putting it together. Okay? So once you view trees in this way, then they become a Frizer class. A Frizer class is something that satisfies this. So that means that there's a limit. Now try to visualize it. Okay? So it's a tree. There's some closest common ancestor, but it's hard to draw, yeah? Because, I mean, for example, let's take this limit which exists by the Frizer theorem. Let's take two nodes in this tree. How many nodes do I have between them? And they're shaped like what? They're ordered in what way? Well, they're not well ordered. Quite the opposite. It's dense. They're like the rational numbers. Because I can always put something here and something here and something here. And so in particular, there's no such thing as a child. Because you take a child, there's somebody between you. You know? There's no such thing as a parent. And then how you have lots of, well, children that don't exist, but if they did, there would be lots of them, yes? So it's hard to visualize this tree, but it's there. It's a very nice structure to think about. Or maybe not think about.
So it doesn't have a root either, right?
It doesn't have a root either. So it goes like, there's a unique, in the limit, a unique path to the top, yes? So if you identify two paths, so take a branch to be, let's define a branch in a tree. Well, I draw it like this, but there's no such thing as this. A branch is like this. So formally speaking, it's a inclusion-wise maximal subset that's totally ordered by the descendant relation. It's a branch. And then if you identify two branches, if they might diverge, but they have a common prefix, then there's a unique branch in this sense, yes? Because every two branches join eventually. Because every two nodes have a closest common ancestor because it's a function. It's a funny structure. It has a decidable MSO theory, for example.
Does it have a name?
I think you can call it the limit tree. Yeah. Or
there are many variants of this tree. There are variants which are binary, there are variants which...
binary ones? Is that?
Consider relational signature.
But I'm not sure if you consider binary trees, you might, I don't see how to get amalgamation. I don't see how to avoid, maybe it's possible, but I don't see how to avoid the problems with paths. But, well, if you think of paths, it's like a successor relation, so.
Because such a binarity is universal, this tree can be embedded in the binarity.
So this tree has, maybe let me, this tree is this is the name that people usually use, universal tree. It has the property, well, by this Frizer limit, it has the property that every finite tree is a substructure. But it has a stronger property, namely every countable tree is a substructure. And let me explain why, and this is true actually just because of homogeneity. So this is part of a general result. Yeah, it's not. So this is this universal tree. And here's some tree. Countable. So I take the first node, then, well, I map it to some node in the universal tree. Okay? Now I take the second node. Okay? Now, if you think about homogeneous structures, a property is that you can extend it to an embedding. And why is that? Why, if I have already, so suppose that I've already mapped part of a tree into so suppose I've embedded a finite tree, such as this one, into the homogeneous one. So I have an embedding like this. This is an embedding F. And now I have some extra node, like maybe this. And tell me why I can extend the embedding F to account for the extra node. Why can I find somebody here? Why does there exist an extension F prime which? So it's a question. Why? So let me just restate it once again. I have a finite structure, in this case a tree, but this is true in general. I have a finite structure which embeds into the Frizer limit. And I extend my finite structure so that it's still in the class. Why can I extend my embedding so that it continues to go into the Frizer limit?
Because you can embed it somehow.
Yes, so I have this structure, say B. This is the finite structure, in general finitely generated, okay? And as Grzesiek says, maybe it's not exactly here, but I can embed it somehow, because the universal structure has everybody as a substructure. So there is some copy of this guy, of the extent of the bigger one. The bigger one with the extended one. There is some copy somewhere here, which embeds. Okay?
Like homogeneity of the universal tree, we can like take this partial function to this copy and extend it.
So there's this part here. This is the image of B, and where B prime is the bigger one. So here it's B prime, which contains B, and here's a copy of B, of the smaller one, yes? By definition of homogeneity, if I map this guy here onto, well, then it extends to a total full automorphism. So this guy gets shifted somewhere here, and his extra node gets shifted somewhere, and that's my extension of my embedding. Okay? So a corollary, maybe the picture was really bad. Now the corollary of this is that if I take the universal, if I take the Frizer, a homogeneous structure, and I have some embedding of a structure B and a bigger structure B prime, these are both finitely generated, and I have some embedding F, then for all F exists an extension F prime of the bigger thing. Okay? And in fact, you can if you think about it, this is equivalent to being homogeneous, but it's a so you're homogeneous if and only if you satisfy this property. Okay? Now, a corollary of this is that you can embed every tree into the universal one, because every countable one, because you just take the first node, you embed it, you add another one, you extend it, and you keep on extending it, and eventually you embed the whole tree. Okay, so it contains all countable trees as well substructure.
Just to be sure, F prime extends F.
Yeah, the picture is F. Let me just type it. It extends F. So F is from B to A, and F prime is from B prime, which extends A, and it extends it, so it's
and it keeps the
and yes, so it extends it in the usual sense. So if you take for arguments from B, F and F prime give the same result. So as it's a subset. Okay. Let's see how much time we've got. When are we supposed to finish? At
5 p.m.
But we start a bit late. 5. So is it okay if we finish in 10 minutes, in 10 or 15 minutes? So maybe one sentence about homogeneous things, and I will continue. I will come back to sets with atoms. The random graph. Think about choosing a graph at random here, in the way that I described before. So you flip every edge with probability 1/2. Will it have this property? So the property that if I embed something into this randomly chosen graph A, and then I have a bigger graph, then I can extend the embedding. Yeah, so to think of it this way. Here's a randomly chosen graph G. And I have some graph and which embeds into a bigger graph. So the bigger graph is all of this, and the smaller graph is just the green part. And imagine I have an embedding of the green part. Well, maybe the picture is kind of bad. I have an embedding F of this green part. This is B. Can I extend it to an embedding of the bigger part, assuming this is a randomly chosen graph? Well, of course, it depends on which randomly chosen graph I have, but I hope it's clear that with high probability I can. Because all I need is, I need 2 extra nodes here, which are connected like this. So, I mean, if I keep on tossing coins, eventually I will find 2 such nodes which are connected exactly this way. It's impossible to avoid this forever. So if you have to state the quantifier's property, but I would say for every such thing, with probability 1, I can extend it. Since there's countably many such things, then with probability 1 I can extend all of them, which shows that if I choose my graph at random, it will with probability 1 satisfy this property here. And from the Frizer theorem it follows that this graph is homogeneous, and in fact it's unique. So that's where the random graphs comes from. Okay. Now let's come back to automata. So you remember we had this minimization algorithm, and let's just illustrate it on one example, and I think that would be the end for today. So consider the atoms are, well, natural numbers with equality. So there's just infinitely many elements, and they're equal or not equal. There's no structure. And consider the following language, L, which is, the alphabet is the atoms. So the input alphabet is the atoms. This is a legitimate input alphabet because it's a set builder expression, or it's hereditarily orbit finite. So you can construct a language like this. So it's words of length, which doesn't have well, it has infinitely many words, but they're all very short. Words of length 3 such that the third letter is either the first or the second, okay? So let's try to come up with an automaton, which is, as by a set builder expression, represented, which recognizes this. So maybe I will do this using something called register automata, and you will see why that works out. So we have states. We have the following. We have states of the form. There's like a control state Q0, and it has 2 registers. And it starts out with, in this state, it reads a letter A. It goes into control state Q1, and it has here, and this register is still not loaded. It reads B, goes into control state Q2. It reads C. Now, depending on what type of C equals A or C equals B, it will go to an error state. No, this is not, no. Otherwise. Here it will go to an accepting state. This is a rejecting state. And here, well, yeah, something like this.
No, so we have to reject the shorter word.
Yeah, but so this is the unique accepting state. And this is the initial state, okay? So that's a natural automaton. I described it using register terminology and control states, but if you think about it, it's you can describe the state space by a set builder expression, yes? So one way to view it is that the state space contains what are the orbits of states? How many orbits of states does it have? So states up to atom automorphisms.
5?
Almost. Yeah, there's 5 things on this picture, so this is why you said 5, and this is generally the right strategy. But there's one slightly 6, because this could be A equals B or A not equals to B. And depending on that, you will get a different orbit. So it has 6 orbits. Yeah? So you can view this automaton as, well, it has a state Q0, which let's call it epsilon maybe. And there's no orbit, so it's not similar to any other state. Then there's, well, these 3 states, this one, and this one. And then there's one orbit. This is essentially one copy of the atoms. So this is a disjoint union, okay? Which represents this state. Then there is, I will put it like this. A copy of A squared, which is a 2-orbit set. Okay, and that's it. Yeah? So 1, 2, 3, 4, 5, 6 orbits. Okay, so you can, this is the state space of our automaton. And then it's clearly hereditarily orbit finite, so it has 6 orbits, and you can also define it by a set builder expression in a natural way. Well, disjoint union, if you have to remember what disjoint union means, but this is no big deal. Okay. Which states are equivalent? I mean, maybe if we try to minimize it, when are states equivalent? Is this guy equivalent to anybody? And equivalent means it accepts the same word. So if you start in that state, then it will accept the same. Is he equivalent to anybody? No. Well, because this is the unique state that can accept a 3-letter word. These guys are, well, you can see, this is the unique accepting state, this is the unique state that rejects everything, so it's non-equivalent to everybody. Let's focus on these guys. Is he equivalent to any one of these? No. So they're all equivalent. But here the interesting things happen. So are they all pairwise inequivalent? And of course, if you take 2 different states here, 1 and 3, then they're also not equivalent for natural reasons, yes? But here there's a non-trivial equivalence relation, yes? So who's equivalent to who? Give me an example of 2 states here which are different but equivalent.
1, 2, and 2, 1.
1, 2, and 2, 1. Okay? And if you will run the automaton minimization algorithm, it will determine this. Because it will compute the equivalent states, and in about 3 rounds or something, it's going to establish all the non-equivalences that we have discussed, and then it will saturate, and after it has saturated, these will continue to be equivalent. Okay? So what is the state space of the resulting automaton? The state space is going to be these original states that I had, these states I used to have. So I've read one letter, and it's this. This state, it says, it's a different one. I've read this is the same letter twice. And this is going to be, I've read, maybe, let me just illustrate them by example. I've read 3, I've read 3, 3, and here it says I've read 3, 2, or 2, 3. But I don't know which, I don't care which one. It's not important, okay? So if you run the minimization algorithm, you get an automaton with this state space. And you can see that you need state spaces like, more fancy state spaces like this in order for the automata to minimize. Okay? So maybe just a historical note. Originally people studied automata like this. I mean, they continue to do so. Which are called register automata. So say you have 2 registers and you have a control state and then you update things in the way you would expect. But this model is not so well behaved because, for example, it doesn't minimize and has other natural constructions go outside of this model. Okay, and we will return to this tomorrow. And I wanted to say maybe 2 more things and then we'll finish. You can come up with even fancier examples. So try to think about this one. A, B, C, A prime, B prime, C prime, such that, I draw it like a picture. What does this mean? This means that the triple ABC is equal to the triple ABC up to cyclic shift. Mm-hmm. Okay, it's a well-formed language. And then you can come up with a register automaton, which essentially uses 3 registers or something. But if you want to minimize it, then by the time it's come here, it needs to store in its state a triple ABC up to cyclic shift. So that's the kind of data structure you would need to maintain. And then you can imagine even more fancy things like, you know, ABC is equal to A prime B prime up to the action of the, I think it's the alternating subgroup of permutations. So it's an even number of transpositions and things like that. We might actually study such things tomorrow. The last thing I want to say is this. This was an example in the atoms which are with equality on. Okay? But you can think of atoms which are the random graph. Why not? And it's a legitimate choice of atoms. It's oligomorphic. It has decided with first order theory. So all of the results apply. In particular, you can effectively minimize automata and stuff like that. And now try to think about automata which work here. And they can do kind of interesting things. So here's one thing you can do. And this would be the last thing I can say. Suppose that the alphabet is the atoms. So these are vertices of the random graph. And say can you do this? A path meaning there's an edge from A1 to A2, there's an edge from A2 to A3, and so on. Yes, you can. What are going to be the states? You start with epsilon. And by the time you've read several letters, what do you need to store in your state?
The last one?
The last vertex. Or, well, there's an error state. Yes, it's not a path. Okay? But otherwise, you need to store the last one. Okay? So your state is a vertex. You can think of it as a register. And what is the transition relation? Delta Q of A, where this is, it's what?
Just edge relation.
Well, it's supposed to be a function.
Yeah, i.e.
they are related at bottom of it.
And if you think, well, this is just, if you just unfold it as a set, is the set of triples QAA such that, well, yeah, Q is which is a set builder expression. That's fine, you can do that. So you can try to now you can, if you have free time, you can start to think about all sorts of crazy automata which input a sequence of vertices in the random graph and check some property of them. And then you can minimize these automata, you can check them for equivalence, and you can all do everything you can do for automata, and now they start to do very strange things. So can you check if it's a clique? Why not? And this, I will not ask anything, just tell me why not. I mean, it has an intuitive reason, yes?
You need to keep all the vertices.
You need to keep all the vertices. You can prove this formally, but okay, so that's it. So, thank you. I mean, I still don't understand properly what properties of graphs you can recognize this way.
But okay, if it is clique, basically the state space would be kind of too big, right?
Yes.
Mm-hmm. Bigger graph that you won't be able to.
Yes. So, and the formalization of that would be, if you need to store all vertices, you would need more and more orbits. But that's